Today, we're going to dive into a pretty wild idea from physics. What if the universe cared only about shapes and not about size at all? This is the world of conformal field theory, or CFT for short, a place where the fundamental rules of the game look the same whether you're zoomed way in on an atom or zoomed way out on a galaxy.
I mean, really think about that for a second. Imagine a universe with no fundamental length scale, no rulers. You could zoom in forever or zoom out forever, and the physics will look exactly the same. What would that even be like? Well, this isn't just some sci-fi concept. It's the very heart of a super powerful field of study. So, this amazing property has a name. It's called conformal symmetry, and it means that theory doesn't just look the same when you zoom in and out. It's also the same if you rotate it or shift it around. It's a physics purely of angles. It's like the universe has an ultimate zoom function, and no matter how you use it, the basic rules never ever change. And that one simple idea, it has some seriously deep consequences. Okay, to really get a feel for this, we're not going to try to bite off the entire cosmos at once. No way. Instead, let's take a little guided tour of the simplest possible universe we can imagine. It's a 2D world run by something called a free scalar field. You can think of this as our own little pocket universe, our laboratory for figuring out the rules of CFT. Every universe needs a rulebook, right? Well, for our little toy universe, this is it. Now, don't get hung up on all the squiggles and symbols. The big idea here is that this one single equation, what physicists call the action and label with an S, contains every single law for how this 2D world works. It's like its fundamental source code. So what's the point of this rulebook? Well, the universe is kind of lazy. It always wants to find the path of least resistance, or in this case, the path of minimum action. And when we demand that this S value be as tiny as possible, out pops the fundamental law of motion for our field. And what does that law say? Basically, that the field wants to be as smooth and flat as possible. No sudden spikes, no crazy wiggles. All right, so we've got our universe and we've got its rulebook, but how do we actually see what's going on in there? How do we measure anything? To do that, we need to learn how to speak its language. And in CFT, that's the language of operators. The way we interact with this field is by sticking in these little mathematical probes called operators. Think of them like tiny sensors that you can place at any point to measure something, like the value of the field right at that spot. But not all operators are created equal. Some are incredibly special. We call them primary operators, and they are the absolute gold standard because they behave in this beautifully simple, predictable way when we start messing with our point of view. So here's the magic of a primary operator. Picture this. You've got your operator sitting at some point. Then you do one of those conformal transformations. You stretch the whole universe or you rotate it. What happens to the operator? It just rescales perfectly. It scales by a factor that depends on the transformation and this one special number h called its conformal weight. That's it. This incredible predictability is what makes them the bedrock for actually doing calculations in CFT. Let's keep building on this. Now that we have our tools, let's ask a really basic question. If we go into our little 2D universe and we poke it in one spot, what does that ripple look like as it spreads out? How does the rest of the universe feel it? The answer, it turns out, is probably not what you're expecting. Now, in physics, the tool we use to measure this ripple effect is called the propagator. It's just a way of measuring the connection between a poke at one point and the jiggle it causes at another point. It's the math that describes how cause and effect spread through this universe. And when you do the math, this is what you get. Again, don't sweat the details. Just look for that little ln symbol. That stands for logarithm. And that, my friends, is where things get super weird. It means the influence from our poke doesn't just fade away quickly, like ripples in a pond. No, it fades away incredibly slowly, logarithmically. It's a ripple that, for all intents and purposes, never really dies. Let's just stop and appreciate how bizarre this is compared to the world we live in. In our normal 3D world, if you make a disturbance, its effects fall off pretty fast with distance. Things settle down, there's a stable, quiet nothingness, a vacuum. But in this 2D conformal world, that logarithm means the fluctuations, the ripples, actually grow the farther out you go. The vacuum isn't calm at all. It's a state that's constantly spreading out to infinity. So, did we mess up the math? Is this just some weird fluke? Not at all. This is a real fundamental feature of physics in 2 dimensions. This refusal of the field to just settle down has a name. As our source material states, quote, this is usually referred to as the Coleman-Mermin-Wagner theorem.
It's a famous result that basically says, sorry, you just can't have certain kinds of physics in these low-dimensional worlds.
Okay, so our simple little universe is turning out to be pretty strange. To really get to the bottom of it, we need to pull out the biggest gun in the CFT arsenal. It's an operator that's so important, it basically governs the entire structure of the theory. It's time to meet the stress-energy tensor.
The stress-energy tensor, which everyone just calls T, is the big boss. It's tied to all the things you want to conserve, like energy and momentum, but its real job is even cooler. It's the thing that generates the conformal transformations. If you think of the whole theory as an orchestra, T is the conductor, telling every single instrument exactly how to play when the very shape of space-time changes. And you can see its power right here. It's like the ultimate diagnostic tool. When you bring T really close to any other operator in the theory, their interaction basically forces that operator to reveal its deepest secrets. You can see in these equations how T just pulls out all the key data, like its conformal rate and momentum. It tells you exactly what you're dealing with. So we've spent all this time playing around in this quirky two-dimensional toy universe. And it's been fun, for sure. But you're probably asking, okay, so what? What's the point? Why does any of this matter in the real world? Well, it matters a lot. For starters, this simple field isn't just a toy model. It's the absolute fundamental building block of string theory. And its weird 2D behavior, it actually shows up in the real world. It perfectly describes what happens to systems right at a critical point, like the exact moment water turns to steam or a magnet heats up and loses its magnetism. And all the tools we've been talking about, they aren't just for this one example. They're used all over modern theoretical physics. So what we've seen is that even the simplest rulebook you can write down can give rise to a universe with incredibly surprising, deeply important, and kind of counterintuitive physics. It really leaves you with a huge question. What other profound secrets about our own universe are hiding right there in plain sight, just waiting to be found inside its simplest looking rules?